All I did was draw a cell, and this just means I'm dividing it into an oxidation side and a reduction side down here. Okay. The ions, for example, say if you're working with a melt, sodium chloride, would be sodium ions and chloride ions floating around independent of one another. The reason sodium has a cationic charge, as we explained when we were talking about the periodic table, it is deficient in electrons. It has more protons than it does electrons. So it's deficient in electrons and wants to gain electrons. And the chloride, which has a surplus of electrons, wants to lose that surplus and go back to neutral in a general tendency. So if we look at the cations, whatever it is, and we're just choosing sodium, it would be, of course, attracted to the electrode here and would absorb one of the electrons here and neutralize. So the sodium would gain an electron and go to sodium metal. And since this gain of electron, that is reduction to the basic standard state. On the anion in melt, in this case, of course, would be attracted to the positive pole of the electrolysis apparatus. And since it has a surplus of negative charges, it deposits or loses its negative charge to that plus surface. So we see the chloride right here goes to chlorine, and when we write chlorine in this equation, it's it's a half reaction, it's called, but we still have to use the diatomic form because that's its basic standard state, and include 2 electrons in that case and balance it over here with a 2 like that. But the chloride in the ionic form goes to chlorine in basic standard state, which is gas form in there. So that's the process. Now, the loss of electron over here, or electrons, is the process of oxidation. And so if you put these together, you will have what we call the net electrolytic net cell reaction, would be the sodium ions plus chloride ions go to sodium basic standard state and solid plus chlorine gas, and I put a circle superscript to indicate that it's back to neutral, which is basic standard state for that substance. Well, I have to balance this with a 2 right there, so that gives me my 2 chlorides and sodium. Oh yeah, I know what. I got to do it this way. I'm showing you the ions. Let me show you them. Actually, it should be written sodium chloride solid, and then I balance here and here. Sorry. That's the net reaction. Well, what I want to ultimately show you here is the change in oxidation state. Here, the sodium is a +1 charge. But when we get over to the product side, right here, it goes to a 0. So it's neutralized. Each one is neutralized. And then the chloride, move that up here. Each chloride starts out as a -1, but then goes to a 0. So the question is, how do you go from +1 to 0? Well, you gain an electron. And that is your reduction side. and you go from -1 to 0, you're losing an electron. And that is your oxidation side. So what I'm trying to show you is once you have this net equation, you can identify the reaction as oxidation reduction by this change in oxidation state. And you can do that with any of the reactions that we just talked about. The carbonates, and we take, say, calcium carbonate, and heat that, it goes to calcium oxide plus a carbon dioxide. Well, over here, this is a -2, overall minus, yeah, that's a -2 oxidation state, -6, net, 2 to 3 is -6. This would be a +4, so -6 plus 4 is a -2, if you recall. That's a -2 polyion. Calcium is a +1 right there. Well, you go over here, that's going to be a -2, +2, -2, and that's a, well, it's still the same. I'm using a bad example, I guess. Calcium, oxygen, oxygen, but they still break down. I know the one. Let me show you the KClO3. That's the one that you heat that, so you have a KCl plus an O2. Here is a -2 right here, +1. Let's see, so that's 2 oxygens, +4. 2 is a -4 overall right there. Okay, and then add back 1. That's a +3 right there. Well, over here it's a -1 and +1. And then your oxygen goes from a -2 to 0 oxidation state. So I'm just trying to illustrate the idea of change. Now, we're going to do this a lot next class and showing you how to, what single replacement reactions are and double replacement, oxidation reduction reactions, metathesis, double replacement. Don't change oxidation. That's not necessarily a metathesis reaction, but I just selected it out of there. But anyway, the decomps still fall under oxidation reduction.